We're going to do a question from chapter 12, question 20. The following data summarize the results from an independent measures study comparing 3 treatment conditions. Use an Anova with an alpha of 0.05 to determine whether there are any significant differences among the 3 treatment means. Note, because the samples are all the same size, MS within is the average of the 3 sample variances. What we're going to do first is we're going to do the step 1 of the hypothesis testing procedure. So we're going to go through that process first. With an Anova, there is no one-tailed, two-tailed situation. And beyond that, your null hypothesis, as always, is that there is no difference. We have 3 treatment conditions, so we have a mu1, a mu2, and a mu3. And the null is that they're all equal. If we had more groups, we'd have to have more in our null hypothesis. So the null does need to be tailored to the number of groups that you have. But beyond that, it doesn't vary. The alternative is that at least one group differs. And that is all the time for the Anova. What the Anova is doing is it's going to compare group 1 versus 2, 1 versus 3, and 2 versus 3, all in one go. And doing that keeps the experiment-wise alpha level at whatever we set it at, in this case 0.05. If we reject the null hypothesis and accept the alternate, we aren't going to know which one of these means these comparisons is significant. They could all be significant. What the Anova tells us is at least one of them is significant. And so to figure out where those differences are, we'd have to do the post hoc tests, which isn't part of this particular question. So this is step 1 of the hypothesis testing procedure. And it can be helpful to record or to label, I suppose, to label each step so that you are less likely to miss a step. Step 2 of the hypothesis testing procedure is that we need to find our critical values, the values that we will compare to, just like as before. In order to do that, we need our degrees of freedom between and our degrees of freedom within. Degrees of freedom between is k minus 1. Degrees of freedom within is big N minus k. And those are the 2 that we need for step 2. I'm going to go back to the question so that we can pull those numbers out. We need K and we need big N. K is the number of groups. We have 3 groups. We can see 3 columns. The question says we have 3 treatment conditions. So K is 3. And we need big N. Big N is equal to N1 plus N2 plus N3. It's the total number of participants across all conditions. In this case, each of our groups is the same size. So it's 10 plus 10 plus 10, because each group is 10. So it's 30. So we can put that number in here, and over here we have minus 1. So degrees of freedom between, we have 3 groups, minus 1. Degrees of freedom between is 2. And I strongly suggest that you have your Anova summary table all ready to go, and that you fill it in as you compute some of these values. What that does is it helps you keep track of what you've computed. It organizes your information and helps you see the relationships between things, because the Anova summary table is organized in a very specific way, a very intentional way. Degrees of freedom within was big N, which was 30, subtract K, which was 3. So degrees of freedom within is 27. We'll come back and finish the rest of that Anova summary table in step 3. What we need is our critical value. To find the critical value, we're going to need to know the F statistic. The F statistic is mean square between divided by mean square within. And what we need are the degrees of freedom of the numerator, degrees of freedom of the denominator. The numerator is mean square between. Numerator is the top, denominator is the bottom. So the degrees of freedom of the numerator is 2, and of the denominator is 27. And so what we do now is we go to the statistical tables that I have loaded up here, and we're going to go to table B4, the F distribution. What we see up here on the top, degrees of freedom numerator, that's our degrees of freedom between the numerator of the F statistic. So the numerator, in our case, the degrees of freedom of the numerator was 2. And then along the side, we have degrees of freedom denominator. That's the degrees of freedom of the bottom part of our F statistic, which is the degrees of freedom within, which was 27. And so we're going to scroll down, and what you see is in each row, there's 2 sets of numbers. There's the light face font and the bold face. The light face's alpha is 0.05, and the bold is alpha is 0.01. So our critical value for 2,27 is 3.35. F critical is 3.35. So 3.35 is going to be the value that we compare to in step 4 of the hypothesis testing procedure. What we now need to do is fill in the rest of this table. Okay, that will be step 3 of the hypothesis testing procedure. And what we're aiming for is to get to this F statistic over here. It's just going to take us a bit of time. And that's the thing with an Anova. In and of itself, each step isn't particularly complicated. The formulas are not overly onerous. There are a lot of steps though, and so it is time consuming. It is certainly time consuming, but doable, right? So step 3, we need to finish filling in this Anova summary table. And I think that the most logical place is for us to finish up with our degrees of freedom. So we need degrees of freedom total. We have 2 options here. We can either calculate it using the formula, which is what I'm about to do, or we could use the relationship between these 3 sources and compute it that way. The formula for degrees of freedom total is big N minus 1, which is 30 minus 1 is 29. We could have also used the relationship that degrees of freedom total equals degrees of freedom between plus degrees of freedom within. And we would have gotten the same answer. 2 plus 27 equals 29. If you look at it, the table, the Anova summary table, is organized in a very intentional way, showing us some of those relationships in the calculations. The sum of squares within, in this case, can be calculated in two different ways because each group is of the same size. I'm going to use the formulas so that we have the basic principles. And we're going to have to use sum of squares between and sum of squares within to calculate sum of squares total. Because the formula for sum of squares total is the sum of the x's squared, subtract big G squared divided by big N. But if we look at the data, we don't have a way of finding x squared. We don't have the x scores to square. We don't have the raw data. And we aren't given this value, because sometimes you will be given that value. But in this case, we aren't. So in order to calculate the sum of squares total, what we're going to have to do is calculate sum of squares between, sum of squares within, and then add those together to get our sum of squares total. And that's one of the things with the Anova questions is sometimes you have to look at what you can figure out and go from there. And you know, it's this puzzle to put together too. So for sum of squares within, that is the sum of the sum of squares. So it is sum of squares 1 plus sum of squares 2 plus sum of squares 3. We don't have the sum of squares, we have s squared. But that's okay, because the variance, s squared, is sum of squares divided by its degrees of freedom. If we multiply both sides by degrees of freedom, what we get is that the sum of squares is degrees of freedom times the variance. And we have the degrees of freedom, that's n minus 1 for each group, and we have the variance. So we're good to go. We're going to need to calculate sum of squares 1, sum of squares 2, and sum of squares 3. So sum of squares 1 is degrees of freedom 1 times the variance of group 1. Sum of squares 2, degrees of freedom of group 2 times the variance of group 2. And sum of squares 3, degrees of freedom of group 3 times the variance of group 3. So we're going to go through and get those numbers. Now, the degrees of freedom, each group has 10 participants. So the degrees of freedom of each group is n minus 1. So 10 minus 1, so it's 9. So we're going to have 9 times some number plus 9 times a number plus 9 times the number. And what I'm going to do now is I'm going to go to that question and get those values there. All right. So let's go do that. So we go here and we're going to need the sum of squares of each of these groups. So we need 2.67 plus, and then the next is 2, and then 1.33. And so I'll stop my share and we'll go from there. So sum of squares within 9 times 2.67 is 24.03. 9 times 2 is 18. And 9 times 1.33 is 11.97. So 11.97 plus 18 plus 24.03 is 54. So that's my sum of squares within. I need my sum of squares between. And this is all part of step 3. Step 3 of an Anova has a lot of moving parts, a lot of calculations. The formula for sum of squares between is the sum of each t squared divided by n, by little n. The little n is the number of participants in a particular group. Subtract big G squared divided by big N. So T is the total for a given group. So we have T1, T2, T3. Little n is the number of participants in that group. So we have N1, N2, and N3. Big G is your grand total. It's all of the groups combined. And big N is your total number of participants. We already calculated big N as being 30. Okay? We need to calculate big G, which is going to be T1 plus T2 plus T3. And so I'm going to go back to that question. I'm going to share my screen. We'll go back to the question and we'll pull those numbers out. So T1 is 20. T2 is 30. And T3 is 40. I also need the n, the little n's, and those little n's, N1 equals N2 equals N3, and they're all 10 each. Big G, 20 plus 30 is 50, plus 40 is 90. And when I come back over here, what this tells me is take each t, square it, and divide by n. So 20 squared divided by the number of participants in group 1, which was 10. T3 was 30 squared divided by the number, or sorry, that's T2. T2 was 30 divided by the number of participants in group 2, which was 10. T3 is 40 divided by the number of participants in that group. So these are added together. That's what this summation symbol says. And then we subtract, big G is the grand total, 90 squared divided by the total number of participants, which was 30. Okay, so now 20 squared is 400 divided by 10. 30 squared is 900 divided by 10. 40 squared is 100. See, I'm glad I double checked. It's 1600 divided by 10. 90 squared is 8,100 divided by 30. Okay. That is the same. That's what equals means. It's the same on both sides. It's not that that's the answer, but on each side it's the same. So I'm going to go, I've run out of space. I'm going to go up here like that. So 400 divided by 10 is 40. 900 divided by 10 is 90. 1600 divided by 10 is 160. And 8100 divided by 30 is 270. Now this last one is a subtract, right? Don't persevere, it's add, the last one subtract. 40 plus 90 plus 160 is 290. Subtract 270, which is 20. Now, your sum of squares is always going to be positive. Each of the sum of squares is going to be positive, and that goes back to how it's computed. The sum of squares is sum of the squared deviations. When we're computing the sum of squares, if we use the definitional formula, we take each score, we subtract the mean, we square it, and then we add them all up. If you square a positive number, positive times positive, positive. If you square a negative number, negative times negative is positive. So your sum of squares is always going to be positive. Your sum of squares total, regardless of how you calculate it, your sum of squares total is always going to be bigger than your sum of squares between and your sum of squares within. That's always, always, always. Whether you use the formula that I showed you previously, that in this case we can't use because we don't have x squared, or if you use the formula that we are going to use in a moment, you should get the same answer. So right now, sum of squares total equals sum of squares between plus sum of squares within. So when we see it like this, and knowing that sum of squares between and sum of squares within are always positive, it's clear with this formula that sum of squares total is always going to be larger than the pieces that make it up, go into it. So we have 20 plus 54. It's 74. So the only way that sum of squares total in theory could be smaller than sum of squares between and than one of those numbers is if one of those numbers, sum of squares between or sum of squares within, was a negative number, but that's not possible. So your sum of squares total is always, always, always larger than your sum of squares between and your sum of squares within. That's just how it goes, always. So now we're going to compute your mean square. Note that there is no line for mean square total. That's just not part of it. We don't compute it. So mean square between is, the mean square is the mean of the variances among the groups, and the mean of the between groups variances in this case. So it is a type of variance. If we go back to chapter 4, variance is sum of squares divided by degrees of freedom. And that's what we're going to do here, except instead of using this symbol, we use MS, and we use MS because it's the mean of those between group variances. So it's sum of squares between divided by degrees of freedom between. And look at this. Sum of squares between divided by degrees of freedom equals the mean square. So 20 divided by 2 is 10. And we'll do the same for mean square within. Sum of squares within divided by degrees of freedom within. 54 divided by 27, which is 2. So we're getting close to that F statistic, okay? And goodness me, on the exam, show your work. Goodness sakes. If you go sideways somewhere and you show your work, your professor is better able to give you part marks. And I always look for ways to give part marks. So your F statistic is your mean square between divided by your mean square within. And again, this Anova summary table is organizing our information for us. It's 10 divided by 2, which is 5. Okay. And there ends step 3. And yes, it is a beast. That's how it goes. But each individual formula is not too bad. I think the worst is when you have to calculate from scratch the sum of squares between. But if you have the right information, you can calculate your sum of squares total and bypass the sum of squares between formula. Bypass it, potentially, depending on what data you're given. In this case, we couldn't. Step 4. For step 4, we need to compare the value that we calculated to the value from our table that we got in step 2. The value in the table was 3.35. And so anything out here, we're going to reject the null hypothesis and accept the alternative hypothesis. Anything over here in this unshaded region, we're going to fail to reject the null. And yeah, I know that the wording is weird. That's how it is. That's how it is when I learned it and I thought it was weird. That's how it still is. That's just how it goes. Okay. So the value we calculated is out here. So we're going to reject the null and accept the alternative. This is our evidence. It's completely sufficient. And then I want you to interpret. I want you to understand what the numbers are. It's all well and good to be able to calculate the numbers, but it's useless if you don't know what they mean. This means that at least one group mean differs from the others. And without post hoc tests, that's all we can conclude. We don't know which groups differ, whether it's one or all of them are different from each other. This is what we can conclude. At least one. It could be just one, could be 2, could be 3, could be any of those. We need the post hocs to figure that out. So now I'm going to pause here. When I come back, we will calculate eta squared, which is the effect size measure for an Anova.